Hello everyone and welcome to my Wave. I'm Shashi and in today's video, I would like to give you a quick introduction to my Wave, the products we offer and some of the exciting applications where RF, microwave and millimeter wave technology are used. Whether you're new to this industry or already working with microwave systems, this video will provide you simple overview of our product portfolio and how these products fit into real-world applications. Let's start with the basic question. What are microwave and millimeter wave frequencies? Microwave frequencies generally extend up to about 30 GHz. Above that, from approximately 30 GHz to 300 GHz, we enter the millimeter wave region. Beyond 300 GHz, we move into the terahertz range. You don't need to memorize those numbers. The important thing to know is that these higher frequencies enable technologies used in radar systems, satellite communications, aerospace and defense programs, automotive radar, scientific research, sensing systems, and advanced test equipment. At MyWave, we design, manufacture products that operate throughout these frequency ranges. Our products can be grouped into three main categories: subsystems and integrated assemblies, antennas, and components. Let's take a closer look at each of them. We will start with the subsystems. A subsystem is essentially a complete functional building block that performs a specific job within a large system. Instead of purchasing multiple individual components and integrating them yourself, a subsystem provides a ready-to-use solution. Next, let's talk about antennas. Antennas are one of the most visible parts of any RF or microwave system because they are responsible for transmitting and receiving electromagnetic energy. MyWave offers many different antenna types, including standard gain horns, conical horns, scalar feed horns, dual ridge horns, horn length antennas, omnidirectional antennas, reflectors, waveguide probe antennas, and custom antenna assemblies. Different antenna designs are optimized for different applications. Some are used for radar testing, some for communication links, and others for antenna measurement and calibration. Now let's look at the components that make these systems work. Our component portfolio includes both active and passive devices. The easiest way to think about the difference is this: active components require power to operate, passive components do not. Active components perform functions such as amplification, frequency conversion, signal generation, switching, or noise generation. Examples include amplifiers, low noise amplifiers, power amplifiers, mixers, frequency multipliers, voltage control oscillators, and phase lock oscillators, active switches, and noise sources. These devices help create, amplify, convert, and control RF signals throughout the system. Passive components don't generate gain, but they are equally important. They help guide, divide, combine, filter, attenuate, or isolate RF energy. These products help RF signal travel where they need to go while maintaining proper system performance. Examples include attenuators, directional couplers and filters, isolators and circulators, power dividers, adapters, transitions, terminations, waveguide bends and waveguide sections. These products help RF signals travel where they need to go while maintaining proper system performance. Now let's look at a few examples of how these products are used in real systems. One example is Radar Target Generation Module. Think of it as a device that creates a fake radar target. Instead of needing an actual aircraft, vehicle, or moving object, engineers can use this module to simulate a target and see how the radar responds. This allows radar systems to be tested quickly, safely, and in a controlled environment before they are deployed in the field. An amplifier makes an RF signal stronger. Low noise amplifiers, often called LNAs, are usually placed near the receiver to boost very weak incoming signals while adding as little noise as possible. Power amplifiers are used on the transmit side to increase signal power before it is sent to an antenna. A frequency multiplier takes lower frequency signal and creates a higher frequency version of that signal. For example, a frequency doubler takes a 10 GHz signal and produces a 20 GHz output. This is a common technique used when generating millimeter wave frequencies. A mixer. It combines two signals together to create new frequencies. This allows engineers to move signals from one frequency to another. For example, a radar or communication system may need to convert a very high frequency signal to lower frequency so it can be processed more easily by electronics. An attenuator does the opposite of an amplifier. Instead of making a signal stronger, it reduces signal power by a controlled amount. Attenuators are commonly used to protect equipment, adjust signal levels, and support calibration and testing. A directional coupler allows a small portion of a signal to be sampled while most of the signal continues along the main path. This is useful when engineers want to monitor signal power without interrupting system operation. A power divider takes one signal and splits it into two or more output signals. For example, a two-way power divider sends approximately half of the input power to each output. Many power dividers can also be used in reverse as power combiners. Waveguide adapters and transitions help connect different types of RF interfaces. For example, they can connect a coaxial cable from a test instrument or amplifier to a waveguide antenna or filter. Without these adapters, many RF components would not be able to connect together. Another commonly used component is an isolator. You can think of an isolator as a device that allows RF signals to move forward while helping prevent unwanted reflections from coming back toward the source. Why is that important? In real systems, antennas and loads are not always perfectly matched. When that happens, some of the RF energy can reflect back toward the amplifier. Too much reflected power can affect the performance and in some cases even damage sensitive equipment. By placing an isolator at the output of the amplifier, those reflections are greatly reduced before they can reach the amplifier. An isolator can also help improve the effective BSWR seen by the amplifier. So if the amplifier doesn't have a particularly good BSWR, adding an isolator can help the system operate more reliably and maintain more consistent performance. Before products are delivered to customers, they undergo performance testing to verify that they meet specifications. For passive components, measurements often include insertion loss, return loss, isolation, coupling, and directivity. For active components, testing may include gain, output power, P1 dB compression point, saturated power, gain flatness, noise figure, harmonics, spurious performance, etc. This testing helps ensure that every product performs as expected in the customer's system. So where are these products used? MyWave products support a wide range of industries and applications, including defense and aerospace systems, radar and electronic warfare, satellite communications, automotive radar, scientific research, testing and measurements, and advanced sensing systems. This was a brief introduction to MyWave and our RF, microwave, and millimeter wave product portfolio. In future videos, we will take a closer look at specific product categories, explain important specifications, and show how these products are used in real-world applications. If you would like to learn more about MyWave products and capabilities, be sure to visit our website and subscribe to our channel for future videos. Thank you for watching, and we will see you in next video.